Peter Bouwknegt, that we talk about subjective submersions, managers, group cohomology, and applications.
Okay, thanks, Paolo. Yeah, first of all, thanks to the organizers for inviting me to present this series of lectures. It's a whole mouthful, but I hope to explain most of it, well, all of it, during my 3 lectures. So I think most of the audience are physicists, so while I'll be doing a lot of mathematics, I'll try not to make it too precise, so I will assume that all manifolds are smooth or whatever is needed to make things work, but not always mention things. But you can fill it in by yourself. That's one of my exercises. Yeah, so today I'll talk mostly about surjective submersions, give some motivation, well, introduce what they are, but if you don't know what they are, and give some motivation why they're interesting. And basically my take on it will be that we do mostly, once we study manifolds and physics, we do almost everything with open sets, but that might not always be the right approach. Surjective submersions is sort of a generalization of doing things by open sets, so doing things locally, and in general also contains some global information. So I'll be clear in my first motivating example. Now in the second lecture I'll talk about T-duality and Gerbes. So Gerbes are naturally defined through surjective submersions, so you'll see the definition. And in my third lecture, we'll apply this to tori, or more generally to toroidal orbifolds. So through group cohomology, it turns out that in a particular case for tori, these surjective submersions are closely related to group cohomology. And in fact, it gives you a very convenient way to actually do calculations. So my take on this will be that surjective submersions, and particularly for tori, will give you a technical apparatus in which you can do concrete calculations, similar to calculations you do with differential forms, but then more generally over the integers. So I will set up a calculus similar to differential forms. And in particular for studying T-duality on tori or torus bundles, this will turn out to be very effective. I don't know if you know anything about orbifolds, I'll quickly introduce them, but one of the reasons surjective submersions turn out to be working more nicely with orbifolds is in general an orbifold is defined by, say, a torus divided by some discrete group, but if you choose an open cover, then in general this discrete group will move one open set to another open set, and it just doesn't work that nicely on the open cover. While if you choose a particular convenient surjective submersion, then you can often lift the group action to that submersion. Okay, so maybe you don't know what a submersion is yet, but so let me just do a motivating example. And I will post the written notes on the web as soon as possible. They're pretty much in draft form still. So let's take a step back. Whenever we do physics, we work usually with an action principle. So maybe some action S in terms of some fields collectively denoted by phi. And we often think of that action as an integral over a manifold of some Lagrangian density in terms of the field phi. And then we calculate equations of motion, etc. But of course, this is just not very precise, because in general, these fields phi are not defined globally over the manifold M. Now, if you do particle physics, you don't really care about it. You work with Euclidean space or Minkowski space, so you can define often the fields over the whole manifold. But if you work with things like string theory, then topology of this manifold M becomes very important. So this is just a hand-waving notation for what you mean. If you want to do it more precisely, well, the fields phi typically live on open sets, so what you would do is you write M as a union of open sets, maybe some collection UI. So U is a collection of open sets, indexed by some capital I. And the fields are then defined, well defined within each UI. So what you want to write down is something like integrals over UI, where the Lagrangian density is defined on UI. But that's of course just local, that doesn't cover the whole manifold M. So there's various ways of making it precise. One way is choose a partition of unity. So partition of unity is a collection of maps from, say, M to R, such that the support of rho I is inside the open set UI, and the sum of all rho i's equals 1. And then you can just insert the rho I here, and sum over I. So the support of each rho I is inside UI, so this is well defined. And then, yeah, essentially you, well, these sets might have overlaps, but the partition of unity associates one particular part of Li to Ui and the other part to, well, the other set it might overlap with. And you can do that if, say, if Li of phi equals Lj of phi on the overlap by symmetries. So if your theory has symmetries, like gauge symmetry, then even though the gauge field is not defined over the whole manifold, but differs by a certain transformation on overlaps, the Lagrangian density might be invariant under those gauge transformations, so it's actually equal on the overlap, and then this makes perfect sense. Now you can of course generalize this, or do it differently. So this is an approach where I've written M in terms of open sets with overlaps. But you can also, say, triangulate M and then just sum over the different triangulations where you might have to pick up boundary terms on the edges and the vertices. Other generalization is that maybe Li phi is not equal to Lj of phi, but differs by something exact on overlaps. That's a situation which occurs frequently as well. In that case, you would have to compensate that particular action by these terms, and these can then be written in terms of boundary terms on the overlaps, etc. So this, for instance, occurs when you calculate the holonomy of a gauge field. So the holonomy of a gauge field is something like the integral over the gauge field, which is not gauge invariant, but on overlaps it differs by a gauge transformation, and if you include that gauge transformation on the overlaps inside your holonomy, then it's perfectly globally defined. Okay. So that's sort of the traditional approach. And then when you start going a little bit further and do examples, the first example of a manifold with non-trivial topology would maybe be a torus. So a two-dimensional torus or four-dimensional torus or whatever, or maybe even a circle. But then, when you look at the literature, nobody does field theory on a torus by covering it with open sets. That's ridiculous. That's, I mean, in this case, you need at least 2 open sets. But if you want to sort of, so this intersection here has 2 open sets. So if you want to avoid that, you need 3 open sets already for the circle. For the torus, you need many more. And if you're just going to calculate those integrals by doing that procedure over open sets, I mean, it becomes a mess. Of course, what we do in the case of the torus or circle is periodic boundary conditions. So you might ask, why do I give that introduction? For the torus, I do it completely differently. So what I'm going to try to argue that is the periodic boundaries is a particular case of a surjective submersion. And for the torus, that this is actually a very convenient surjective submersion. So what do you do? What are periodic boundary conditions? So let's do it for the circle. So periodic boundary conditions for the circle, say if I look at a function on the circle, I think of it as a function on R, where R lives over the circle by the map, say y maps to e in the power 2 pi iy. I think of the circle as the unit circle in the complex plane. So a function on the circle, say a z-valued function, but I don't know, it could be r-valued or u1-valued, whatever you want, is given by a function f from r to z, such that fy0 equals fy1 if y0 minus y1 is an element of z. These are that's what I mean by periodic boundary conditions. If y1 differs by y0 by an integer, then of course it maps to the same element of S1. So functions which are satisfying this condition can be identified with functions on the circle. That's what you mean by periodic boundary conditions. So let me rephrase this a bit. So first of all, I can think of course, of y0 minus y1, that this is equivalent to saying that, I need this again, call this map pi, is equivalent to saying that pi y0 should be equal to pi y1. They should map to the same point on the circle. Okay, so let me introduce something which is called a fibered product. So, do it more generally. So y in my case is just r. In general, it would be some surjective submersion. So a fibered product of such a situation is, well, the fibered product of 2 elements in y is the set of elements y0, y1 in the Cartesian product. So this is y cross y, such that pi y0 equals pi y1. So it's fibered over the base by saying that these 2 elements in y in the 2 copies of y should map to the same element in the base. So that's just another way of saying this situation over here. So f y to, well, say r to z defines a function f s1 to z if if fy0 equals fy1 for all elements in the fiber product. I'm doing nothing serious here, I'm just rewriting it, but in a way that I will generalize it easier. Now it turns out this condition here can also be written as, well, something like this, of course. I'm not doing anything here, but this turns out to be a particular operation which is called a, well, this is called a differential. It turns out that this particular difference is one particular, well, one particular form for the differential here given on functions, but I can extend this to higher order functions given on iterations of, well, higher iterations of these fiber products, and that they form a cohomology theory. So this differential, I haven't defined how it works on higher functions, but it turns out to be satisfying del squared equals 0. So if you apply it twice, it gives 0, so this gives rise to a cohomology theory. So it turns out that you can reformulate this whole thing of what are functions on the base in terms of functions of some, in this case, R, in terms of some cohomology theory. And in fact, you can generalize all sort of objects you want to define on the base manifold M in terms of objects on the surjective submersion in terms of cohomology theory or generalized cohomology theories. Okay, I hope this is clear so far. So this is a bit of a motivation why you might want to think more generally than just open coverings. Clearly for the torus or for the circle, this is a much better way to think of the circle. You can easily describe functions on the circle. You don't have to cover it by open sets and say a function is something that is equal on the open sets, etc., on the overlaps. Okay, so I think this is a good point to start talking a bit about more general surjective submersions. Are there any questions so far? Yeah. Yeah, so my hearing is not very good, so I have to come a bit closer.
No, I was wondering whether it suggested an alternative definition of manifold.
No, I keep the manifolds as they are, but I changed the topology. I'll come back to that. And it's really too mathematical to talk about in these lectures, but I'll make some remark about what the proper context is in the math language. Yeah.
This differential satisfies the Leibniz rule?
Well, yes, but I haven't told you what the multiplication of those chains are, cochains are. So I have to introduce the cup product, and the differential satisfies the Leibniz rule on the cup product. Yeah, I'll come to that. Yeah.
So this condition, f of y0 equals f of y1, or if this pair is in y2, this should hold for every y0, y1.
It has to hold for every in the fiber product in y2.
Oh,
Sorry, this is a for all.
I thought this was the logic symbol or.
No, sorry, this is a for all.
Okay.
Thanks. Yeah, if I have to write louder, you have to tell me. Okay, so surjective submersions is something that you basically learn in any course on manifolds, I think. I hope people have seen it, but they might not have put too much emphasis on it. So I'll just give you some properties and definition of surjective submersions. And as an exercise, I urge you to look up a book on differential topology to go over the proofs and to see if you understand all the concepts. So that's an exercise. But okay, so so definition. So again, I work with smooth manifolds. I work with maps which are smooth maps. If they're maps between manifolds, if they're not manifolds, I'll take as much niceness as I want. So if I look at maps from, say, manifold to integers, I want them to be continuous, etc., etc. So the definition of a surjective submersion between manifolds. So let pi be a map between manifolds, so a smooth map between smooth manifolds. So if the differential, so the differential at a point x, or a point y, say, in y, maps the tangent space at y to the tangent space at pi y. If this map is surjective, for all y and y, then pi is called a submersion. Or if it's surjective at a particular point, it's called a submersion at that point. And of course, if pi itself is surjective, if in addition, pi itself is surjective, then pi is called a surjective submersion. Okay, so I don't know what notation people use for the differential of a map. So sometimes books use the notation pi star. And I might mix up the notation, so please ask if you don't know. So maybe a little bit why such surjective submersions might be interesting. So what I'm trying to do there is to basically represent all the points and differentials on S1, or more generally on M, in terms of things on Y. So if the map is surjective, then of course every point in M is represented by at least one point in Y. But if the differential is surjective, it means that all vector fields on M can at least be obtained by a vector field on Y. So basically these surjective submersions contain all the information about the points in M, but also about the vector fields, but sometimes in multiple ways. And of course, those multiple ways have to be accounted for by some condition like I've done here. Right. But it turns out that surjective submersions have lots of interesting properties which make them particularly interesting. So, but maybe first a few examples. Okay, so the first example is very obvious. So if K is bigger equal L, then I can define a surjective submersion from Rk to Rl. These are just trivial manifolds by just saying I map a point x1 to xk, so in the coordinates on Rk to the first L coordinates. So that should be obvious. If that's not obvious, then please, as an exercise, check the definitions. Okay, the second example is pi, say, from R to S1. That's the map that I've written down there. That's a surjective submersion. Or more generally, I can do the same for pi from Rn to the n-dimensional torus. Okay, well, again, clearly surjective. That it's a submersion, well, you have to calculate the tangent map, but that's easy to do. Also an exercise. And this is actually a special case of something more general. If well, a principal G bundle pi over M is a surjective submersion. Okay, so we have lots of bundles, principal bundles over manifolds M. They all give rise to surjective submersions, so they all give rise to examples that I can work with. And in fact, well, you typically think of, in gauge theory, you think of principal G bundles as for some Lie group G, but in fact this is a principal Z bundle. So Z acts on R by translation, and you can easily check that this is a principal Z bundle. So in fact this example falls also under this more general thing. And in fact, you don't need to take principal bundles, you can also take vector bundles. So Tm to M, a vector bundle, is also an example of a surjective submersion. So really there exist a lot of examples of surjective submersion. And the last one, maybe the one that I argued is not always that useful, is an open cover. So if U is an open set, collection of open sets, such that M equals, well, M is covered by set UIs, then Y of U, so Y is my general notation for a surjective submersion. This one is related to this open cover U. If I just take the disjoint union, it turns out that's a surjective submersion. If the open sets don't cover M, then there's still a submersion, but of course to be surjective you have to cover the whole set M. Okay, this disjoint union looks complicated, but let me just draw a picture. So if here's M, and M is covered by sets UI, so U1, U2, which might have overlaps, then the disjoint union is just taking those open sets and making them disjoint. So this is the collection of, well, this is Y. So for instance, Y2 of the fiber product related to an open cover, so it's all the points, do I still have it here? No, it's all the pairs of points that map to the same base point, but mapping to the same base point in UI and UJ means that it should be sitting in the intersection. So here the fiber product of the surjective submersion given by an open cover is just the disjoint union of the intersections. So saying that something should satisfy something on the fiber product is saying that something should satisfy something on intersections. So that's the sort of standard way you deal with gauge theory. You patch things together globally by by saying how things should behave on intersections. But this is sort of the formalism in terms of surjective submersions. And again, as I said, so this is really a local approach where you patch things locally. This R is really something globally. So if you work with a surjective submersion R, then you have more control over how things behave globally. And that's precisely the statement that things should satisfy periodic boundary conditions. Okay. I hope this is clear so far. So all the details here are given as exercises. This is really the sort of trivial part. Okay, so I've given you a set of examples. Now I want to write down a little theorem which essentially tells you that all surjective submersions are given locally by your first example. So the statement is, this is called the local submersion theorem. So let pi be a surjective submersion. Such that pi y equals x. Then there are just local coordinates. So I'm assuming you know a little bit of manifold theory because I'm not going to write out everything. Around y and x, such that locally pi x1 xk equals x1 to xl. So that locally that submersion is given by that statement. Okay, so if I would write it out more precisely, I have to say local coordinates, so there exist charts in a neighborhood of y and another neighborhood of x, mapping to rk and rl, such that in those local coordinates the map is given by this. But so I have to put in the coordinate charge in this definition. But anyway, I hope it's clear what I mean by this. Okay, so all these examples you can, well, for instance, the principal bundle, you know that on open sets they have to be given by a local product of the base manifold and G, and you can work it out that you can find those coordinates. Okay. So again, this is an exercise, maybe not something you want to prove from scratch, but I want you to look it up in a book, maybe. This can be proved by, what's it called, the, okay, the name escapes me, the, yeah, the inverse function theorem. It's called the. I'll come back to me. But anyway, it's also this is like the rank theorem or the. Okay, it'll come back to me. Sorry. Yeah, inverse function theorem. Yeah. It's like the first theorem you learn if you do differential topology. Okay. Maybe a nice little lemma. So I want to give you some idea how general these surjective submersions are and what they sort of typically look like. Now in fact, so if pi m, the statement that pi is surjective is actually often comes for granted. So if this is a proper submersion, and m is connected, then pi is surjective. Now, this is a bit of topology, but so proper means definition is that the inverse image of every compact set is compact. Okay, so I want to list a set of properties which are the reason why surjective submersions are interesting. But first I would have to tell you what a morphism of surjective submersions is. Maybe I won't write it in words, I'll just draw a diagram. So if I have two surjective submersions over M, then by a morphism I mean a smooth map between smooth manifolds in such a way that this diagram commutes. Okay. Okay, so properties of surjective submersions. So I'm going through a lot of little details, but I hope to sort of convince you that that we should all be thinking in terms of surjective submersions, that thinking in terms of open sets is in general cumbersome or maybe not very well adapted to the problem you want to study. So I hope that at some point all physicists will think in terms of physics given by surjective submersion. So that whole textbooks will be rewritten and that everybody will use this language. So you'll be the first to be my adaptive audience. Okay, so a lot of them are straightforward. The rest I'll give as exercise. So diffeomorphisms, that's the first property. Diffeomorphisms are surjective submersions. Not very interesting ones. But so composition, if you have two surjective submersions, say pi tilde from y tilde to y and pi from y to m. Maybe I'll now abbreviate it as SS. Then the composition, so pi after pi tilde from y tilde to m is also surjective submersion. So you can do compositions of surjective submersions. You should think of this as maybe taking the refinements of open covers. Third property is you can do something like pullback. So if pi, say from y to n, is a surjective submersion, and F is a smooth map from M to N, what you can do is you can construct a pullback manifold. That's just too high. Which is usually denoted by y cross m over n. So again, a fiber product of some sort. Let me call this ym, which is the points ym in the Cartesian product, but such that they agree when I map y to n, and when I map the point m also to the manifold n. Maybe this, I should draw a little picture. So I have a map, a surjective submersion y to n. I have a map f from m to n. Then I can construct this surjective submersion. I didn't make a statement. Okay, so this is a smooth submanifold of y cross m, and the natural projection called pi tilde of ym to m. So just projecting on the second factor is a surjective submersion. Yeah, so you can pull back this submersion to a submersion over m by taking the Cartesian product of y and m in such a way that the point here maps to the same point in n. This is sort of a standard construction. This is called a pullback or associated construction, different names. Okay. Maybe it's useful to try to write out what these things mean in terms of surjective submersions given by open covers, and see that indeed open covers satisfy those properties. We'll have a few more. I'm a bit hesitant to write them all out, but this is an important one for any surjective submersion pi y to m. There exists an open cover U, so given by a collection of open sets of M, and a smooth map S from the surjective submersion given by the open cover to the surjective submersion at hand, such that this is a morphism of surjective submersions, such that that thing holds, so that pi after S equals pi of the open cover. Okay, so this is an important one because it basically tells me that if I have a surjective submersion, I always have a morphism from the surjective submersion given by an open cover. So I can always sort of compare that surjective submersion to a surjective submersion by an open cover. And in some sets it tells me that even though surjective submersions seem to be a bigger class of structures I can put on a manifold M, in fact, it's not really a stronger statement because I can always choose an open cover which compares it to that surjective submersion. Okay, Now 5 I'm probably going to skip. It's a whole list of properties which basically essentially tells you that certain maps are smooth if they're smooth on surjective submersions, etc. It's a whole list of properties. It's not something I'll probably be using. But I want to make a remark. Okay, so if you try to see if these things exist in mathematics, what you quickly find out is that, well, essentially properties 1 to 3 imply that that there exists a structure on the category of smooth manifolds, and that structure is called the Grothendieck topology. Surjective submersions give a Grothendieck topology on the category of smooth manifolds. I'm not going to give you the definition of a Grothendieck topology. I'm just going to, if you're interested and you're a mathematician interested in sort of algebraic geometry, these things show up in étale cohomologies and things like that. Their standard reference is Grothendieck's 7-volume, what's it called, Seminar Grothendieck Algébrique or something. So this is tough stuff, but I'm just going to give you the name so that you do realize it has some context. Yeah, so in particular for these Grothendieck topologies, so these generalized topologies given by open sets, in this particular case, because of the other properties that I've listed, this topology is actually not stronger than the topology of open sets, because you can always find covers which produce the same, essentially the same topology. In general, they don't have to be equivalent to topologies of open sets, but but the essential thing is that if you have a Grothendieck topology, you can basically set up a machinery similar to what you do when you have open sets. So when you have open sets, you introduce a cohomology theory called check cohomology. I'm not sure how many people are sort of familiar with the words that I'm saying, but when I say check cohomology, I assume you have some basic knowledge of algebraic topology. For instance, the book by Bouwknegt 2 is a good introduction. That introduces a lot of concepts related to open sets. If you don't know it, it's not a problem, because I'm going to introduce most of those concepts in the context of more general surjective submersions, and open sets is just a particular example. But if you do want to sort of look at the book by Bouwknegt 2, you can sort of see the parallel in the way I'm developing the theory here. So that might give you some motivation. Okay, so what I can do with these Grothendieck topologies, I can introduce sheaves, well, whatever algebraic structure you might want to introduce. And you need those sort of axioms to do that. So you can talk about sheaf cohomology in the context of the Grothendieck topology, etc. I'm not going to do any of that. I'm just going to be very hands-on. I just want to, as a little aside, I just want to warn you that most of the examples which I've given, it seems that these surjective submersions are the same as vibrations, or maybe locally trivial vibrations. But in fact, they're not. So I want to just, as a warning, say what the definition of a locally trivial vibration is. So a locally trivial vibration, pi y of m, is a smooth map, of course. Such that for each X in M. There, well, there exists a neighborhood, so local. U of X such that there exists a, well, so that exists a map from the inverse image of that neighborhood to U cross F for some fiber. So that's what you have in the case of a fiber bundle. And 2 is, well, that this map should commute with maps to the base manifold. So this should be a commutative diagram. This is U, sorry. Now, not all locally trivial fibrations are surjective submersions, and not all surjective submersions are locally trivial fibrations. But there's, of course, a large intersection, and you might want to have one theorem in that context. It's called the Erisman theorem. So if pi ym is a proper, so inverse images of compact sets are compact, is a proper surjective submersion. Where's my theorem go? Then it is a locally trivial fibration. Okay, so let me just give you one example of a surjective submersion which is not a locally trivial fibration. Well, let me first give you an example of a, let's say, something which is a locally trivial fibration. So the strip, say from -1 to 1, and here R. So this is just R cross, well, the interval -1 to 1. And if I take the projection on the real axis as my map, so here's the real axis. So all the points in the strip map to x1, map to R. Then this is a surjective submersion and a locally trivial fibration. Obviously, this is my prime example where I just map on the first coordinate. I've now compactified the second coordinate so that I want to say something about inverse images of compact sets. So how do I can easily modify this example to still have a surjective submersion but no longer a locally trivial fibration, and I do that by just omitting a point. So if I take out that point, so if I look at R cross -1, 1, and I omit the point 0, 0, well, everywhere away from 0, things stay the same, but of course, everything above the zeros, I still cover the 0, but I also cover all vector fields because there's only one direction of vector fields to cover. So this is still a surjective submersion, but clearly at this point there's no neighborhood so that locally it's U times this fiber -1 to 1 because I have that omitted. And clearly also the inverse image of that point is now consists of two sets which are not closed anymore, so not compact. So the inverse image, so the map here, if I omit a point, is no longer proper. So the theorem doesn't longer hold. But So you see that. So surjective submersions can often be just modified by taking out points.
Where do the points map to?
Sorry, I was a bit quick. So pi from r to minus 1, 1 to r is given by pi xy equals x. So this whole strip maps to the r-axis by forgetting the y-coordinate.
Yes, in the example which is not considered the submersion,
In this case, the map is just the same. I just take out the point 0, 0. So the map stays the same. So I still cover that point because all the other points still map to 0. And I clearly also cover all the vector fields still. They're all given by vector fields and points above it. Yeah, so it's sort of a trivial modification, but you see here the subtlety and the difference between locally vibrations and surjective submersions. Okay, so this was I think my first hour. So next hour I want to set up a cohomology theory for surjective submersions, which is analogous to check cohomology, and it satisfies almost all of the properties of check cohomology. So if you know about check cohomology, you can immediately see the analogy. If you don't know about check cohomology, you'll learn it as a particular subcase of what I'm doing. Okay, so lots of little exercises. This is all sort of standard material which you can find in textbooks. So the exercise is just to look up a textbook, and at the first chapter, manifold theory, you'll usually find proofs of these statements that I made. In the notes, I'll give you maybe some specific reference to specific textbooks that you might want to consult. So let's take a 5-minute break. Okay, just a little correction, which was pointed out to me. The pullback manifold, I put a pi over here, but of course that should have been a f. I compare pairs in here, and I divide out, so I look at the submanifold of pairs in the Cartesian product, which map to the same element in n. So that's what that says. I had a pi here, but that was a typo. Okay, I'm not going as fast as I thought I would. Which probably means I'll be talking about surjective submersions a bit more tomorrow as well. But that's okay. Okay, and I want to talk about the next chapters. So I'm going to introduce a cohomology theory, and by lack of name in the literature, I call it submersion cohomology. But if anyone does find a treatment of this cohomology in the literature, as I said, it's just a particular case of what you can do with Grothendieck topologies. So there might be a particular name for this one already, but for the purpose of my lectures, this is called submersion cohomology. So I'm going to set up a cohomology theory. So I have to set up a set of cochains and a differential. And what I need is the iterated fibered product. So I've given you what the fibered product for two pairs of elements in Y is, but I will need the p-fold iterated one, but this is the obvious definition. Okay, let me label from Y1 to there's going to be some degree shift at some point. So this is the submanifold of the Cartesian product in such a way that all the elements map to the same element in the base. Or a shorthand notation would be fibering over the manifold M p times. Okay, so now I'm going to be using a set of cochains. So cochains, for me, I will note them as p cochains, so the degree of the cochain is p. So they're given by surjective submersion, so let me, in that notation, introduce both y and m. So y to m is a surjective submersion, and then I need some coefficients. Now, as I said, I won't be introducing anything like sheaf theory or anything complicated. For me, the coefficients are, in general, just integers, or maybe the real numbers or complex numbers, or maybe just u1 valued. But so in general, just locally constant sheaves. But as I said, I won't use sheaf language. So these are functions from the p plus 1 fold private product to f. Now I will take f to be an abelian group, and I will write the operation S plus. But of course, if you work with U1, you might want to change all my operations by multiplication, depending on your preference, but I need to use some notation. Okay, so these are my cochains. And again, I take them to be, well, smooth or continuous, whatever is appropriate for my coefficient field. And then I can define a differential. From p cochains to p plus 1 cochains. As follows. So I take a p cochain, then I have to tell you how it behaves as a function on, well, Cp plus 1, so the p plus second fiber product. So I have to tell you how it acts on p plus 2 variables, which for convenience are labeled from 0 to p plus 1. And, well, the formula is not that hard. I sum from 0 to p plus 1, minus 1 to the power I, and I take y0, y1. I leave out the yi, so my white hat here means omission, and I do that with an alternating sum. So the first coefficient, that's why I start labeling from 0, just comes with a plus sign. That's a convenient convention. And indeed, f was something that lives on p plus 1 variable, so if I omit 1, I can evaluate f on that. So in particular, say f, so for p equals 1, now p equals 0, then I have a del f y0, y1, and that's just given by y1. y1 is the first term where I omit the y0 minus fy0. So this is what we've seen before, right? For functions on the real line defining functions on the circle. Okay, claim. And this is an exercise, a real exercise. Del squared equals 0. So del is indeed the differential. Remark, if y is yu, so if y is the submersion given by an open cover, then del is the check differential. So if you know what it is, you probably see this right away. If you don't know, then look up button 2. And just compare their formula with my formula. You'll see it's exactly the same formula, but then the fiber product is the is the intersection, the multiple intersection of open sets. And then the omission is then leaving out one of the open sets. So really this is a straightforward generalization. The exercise is just combining the right terms. It's not particularly hard, but I think if you want to work with these, then this is one of the things you want to try to do for yourself. Okay, so this defines a cohomology theory. Which I call submersion cohomology. So in the usual way, HP of ym with coefficients in f is the kernel of del from Cp to Cp plus 1 over the image of del from Cp minus 1 to Cp. Right? Del squared is 0, implies that the image is sitting inside the kernel, certainly as a vector subspace. And this is just the usual definition of a cohomology related to that differential. Okay. So ultimately, of course, I want to show how useful this definition of cohomology is. So maybe I want to compare it to check cohomology, or I want to sort of see how much this cohomology depends on the particular submersion that I choose. But here's sort of a little exercise, but maybe I'll do that just to make you a bit familiar with the terminology. So if there exists a global section, so S from M to Y, then I claim the submersion cohomology is just 0. So if you have global sections, then these submersion cohomologies are not particularly interesting. And I'll give you a proof, just to see how you work with this. Okay, so let me just say that G is an element in Cp. So this is a cochain of degree P. I want to show that if this is a cocycle, then G is actually a coboundary. Right? Then I've shown that the cohomology is 0. So let me just work out what that means. So 0 equals del G. So del G in y0 up to yp plus 1. I'm just copying that formula, which is still there. Yeah. So this is minus 1 to the I. G y0, leave out the yi, up to yp plus 1. So I can put the first term on the other side. So I also have G y0, so that omits the y0, y1 up to yp plus 1 equals sum, so this is a sum from 0 to p plus 1. This is a sum from 1 to p plus 1, minus 1 to the I, g y0, yi, yp plus 1. Okay, so I haven't really done much. I've just massaged the condition that del g equals 0. But what I want to do is, I basically need to show that g is the del of h. So now I've isolated one particular form for g. So I want to show that this is the del of some other function. So you just specialize to, so the pi of y0 all the way to the pi of, since it's in the fiber product, is the same element x in M. So we just specialize this equation here to y0 is the s of x using my global section. Then, and define h of y, well, h of y1 to yp just as the g of s of x of y1 to yp. See, this is not an extra variable because the x is the projection of all the other ones. So that's included in this definition. But then you see that, well, then you see that this is just a definition of del h. Right, so that's actually a very trivial proof, but it gives you some idea what sort of these submersion cohomologies measure. They really measure cases where the submersion is not sitting sort of as a trivial vibration over M. It's really sitting there with some topology so that I don't have global sections. Okay, well, I hope this find amusing. Go through the details. If it, I've left out some words, but hopefully it's not that hard. So there's two obvious questions. So how does this submersion cohomology depend on the submersion? And second question maybe is how is HP related to check cohomology? Well, maybe that's the same question because the check cohomology corresponds to the cohomology where the submersion is just the submersion by open covers. So these are questions which I'd like to answer. So we can compare different surjective submersions through morphisms. So if S is a morphism of surjective submersions, of SS, well, then of course we can look at the cycle cochains over Y and Y tilde, and we can just pull back the cocycles by using this morphism. So then we have a map as star, which goes the other way. So the pullback, just given by the pullback on cochains. Cochains are functions. You pull them back by applying this morphism. So I have this map between these cohomology theories. So my questions basically are statements about this map. When is this map an injection? When is it a surjection? Etc. So these are questions which I'd like to answer. It turns out that in general this map can fail to be injective. It can also fail to be surjective. So all possibilities are there. In particular, I want to apply this to a morphism which I always have. I told you that for any surjective submersion there exists an open cover, so that I have a morphism of surjective submersions of this type. So I always have a map from a given surjective submersion to the cohomology given by an open cover, which is the check cohomology. Well, I should be a bit careful. I mean, is the check cohomology correspond to that cover? If I want to have the cover-independent check cohomology, so the sheaf cohomology, I need to take a finer and finer cover. So I need to take refinements and refinements. So it's kind of an inductive limit. And you reach your limit point, for instance, when U is a good cover. A good cover is a cover where all the sets and intersections are contractible. But you have this map for every cover. But in order to compare it to check cohomology, maybe I have a notation, check cohomology of M with coefficients in F. I need a particular cover to compute the check cohomology. So in general, a good cover would be sufficient. Okay.
The theta is on the other side. When you speak of the pullback.
The tilde is on the other side? Yeah? Is that what you...
Is it correct?
Yeah. If S works on manifolds, it acts on functions as pullback. Okay. Okay, so here's a theorem which I'll prove for you, and then it's part of this comparison. If S and T are both morphisms of surjective submersions, then, so for the same y tilde, then S star equals T star. So then they give the same map on cohomology. So whenever I have two surjective submersions, I don't have to worry. Well, I just have to find one morphism between them, and then I can compare the cohomologies. It doesn't matter which morphism I choose. And maybe, so this is a particular case of, so if I have open cover, so so this you find in the textbooks. Well, not in Bottom 2, I think, but in other textbooks. And V is a refinement of U. So a refinement means there exists a map, rho from J to I, such that V of j to I. Such that each of the Vj's is sitting in some u, and that some u is given by the map rho. Then this rho gives me a morphism of surjective submersions from yv to yu. So in particular, I have this map from the check cohomology given by the open cover U to the check cohomology given by the refinement. And this you use to do the sort of inductive limit, going to finer and finer covers, eventually ending up with a cover that produces this check cohomology. Then actually this map, what it says here is that this map doesn't depend on the particular element U that I choose to put V in. Might very well be that V sits in different sets U, but it doesn't matter. This map on cohomology stays the same. Right, so that's a very important property. And it's not at all obvious if you think about it. Why should this map not depend on the particular morphism that I choose, or on the particular refinement that I choose? So the proof is by some standard trick in algebraic topology. Okay, so here's the proof. So we're gonna introduce another operator, HP, from CPY. I leave out the M and the F just to simplify my notation a bit, which lowers the degree by 1. And I'm going to give you an explicit formula. So I have to tell you how it acts on elements in here. So this is called a homotopy, or it turns out to be a chain homotopy between the different complexes. So this is by definition so I apply S to the first I elements, and then I copy the ith element, and I apply T to all the other ones. So this looks a bit like a mysterious formula. Sorry. IP minus 1. And there probably should be a sign there. So I take the G and apply S to the first I elements and then T to the last elements, but I copy that middle element. And then I take the sum over all possible positions of I. Now this looks like a strange formula, but let me draw a picture. So here's Cp minus 1 of y. I have the delta, Cp of y, delta Cp plus 1 of y. And I have the same complex, but for the y tilde. So I have my S star and my T star. They're both acting between the cochains by pullback. S and T were both morphisms between y tilde and y. And then here's my yp, HP, sorry, here's my HP plus 1. So they act by lowering the degree. And I claim So I claim, well, this is a straightforward algebraic check, but it's a nice formula that if you if you first apply HP and then delta tilde, you end up here. You can compare this to first applying delta and then HP plus 1, which also ends up here. So they are both maps from here to here. It turns out that that map is precisely the difference between T star and S star. So then, if G is an element of CPY, which is closed, you can just apply it. So then it follows that T del star G minus S star G is, so this term gives 0, and this gives the delta tilde of HP on G. So it tells you that the difference is indeed a co-boundary in the cohomology over here, so that they map to the same point in cohomology. Right, so this, yeah, sorry.
I don't understand this definition of HP. So the right-hand side, the G takes P plus 2 arguments, or P plus 3
P plus 1 arguments. Y0 to Y, P minus 1 is P.
Always P minus 1.
This is P minus 1, yeah. Those are the elements I have here. So it takes P values here, it takes P values here, but it acts on a thing which lives in 1 degree higher because I copy 2 of the elements. Sorry? What should be P minus 1?
HP of G
Yeah?
should be a function of CP minus 1 by P.
Oh, yeah, sorry. This is what you want to have? No. No. No, sorry, this is okay.
No, on the right.
The right board?
HP sends the function from CP to
Yeah.
CP minus 1. Right? And so HP of G should have
Oh,
minus 1. If you put 1, 1,
yeah, okay. So CP, no, CP, P values, yeah, sorry, this should have had P. Yeah. No, it was all right, okay. All right. So HP on G should be acting on P values, which it does here. Sorry, I think it's correct. It's easy to get confused about this, so that's why I urge you to all check these formulas. Okay, let me see if I want to prove this or whether I leave that as an exercise. I've given you the formula, so in principle it's just straightforward. I think I'm going to leave that as an exercise. And you can also see whether I made any typos in there, but I think it's okay now. The solution is in the notes, so, but I think it's useful to try for yourself. I mean, this is sort of, yeah, to me, this is sort of a miracle. Once you find one morphism between surjective submersions, you can use that submersion, you can use that morphism to compare the cohomologies, and it doesn't depend on the particular morphism that you've chosen. Maybe it's sort of obvious for refinements that it shouldn't matter, but otherwise you would probably say, well, then check cohomology is not well defined. But yeah, and the proof is quite, well, you have to sort of guess this formula. You can find it in the literature. I myself just did it for p equals 0, p equals 1, and then just sort of guessed the formula and then proved it. But later on I found that formula or at least for refinements I found in the literature. So it's not particularly new, but it's interesting. Okay, so that's one thing. Now I also want to check whether, well, want to answer the question whether this map is surjective or injective, or neither. And I might put it in the notes, but it's too technical, so I'm not going to go through it here. I just want to say that if you want to compare these two cohomologies, what you typically would do is to go to double complexes. So I would define a double complex as functions from, well, functions from p-fold copies, p+1-fold copies of the first complex, q+1 copies of the second complex to f. So then I have two differentials. I have a differential that acts on the first, and I have this differential that acts on the second. And I can actually make it into sort of Deligne type complex by taking a total differential. So this is sort of standard stuff. So this is also a differential. So what I'm essentially doing, and you can find these techniques in Blot 2 in other cases, you're comparing, maybe you see that if I take Cp minus 1, if I take the Q minus 1, then I just have Cpy, and if I take the minus 1 here, then I have the Cq of y tilde. So particular rows and columns in this double complex give you the cohomologies, give you the cochains I'm interested in. So if you have P here and Q there, you have to see, well, you have to see, say, P minus 1 things here, the C minus 1 Q things here, and here you have the other CPQs. Now if you want to compare one element here to another element here, so if you want to look at the above map there, you have this map S star, and you're basically going to analyze that map by zigzagging through that double complex. So this is the way you can compare Čech and the Ram cohomology, for instance, but you can also analyze this, whether this map S star is surjective or injective.
So you don't need to fiber that product, the y1 this.
Yes, you do, sorry. I think I do want to fiber that. Yeah, thank you. So I think I'll put some details in the notes, but the upshot is you can find quite concrete conditions for when these maps S star are surjective or injective. It basically has to do with being able to solve the zigzagging in this double complex. Now, maybe these conditions are not easy to use in practice. For low P they are. Yeah, you can play around with it a bit, but essentially this is solved. Okay. I should probably say most of what I've been describing here is work done with my honor student Gianni Gagliardo. Who's currently at ETH and is going to do a PhD in Harriet Watt soon. And most of tomorrow and the day after, no, not tomorrow, the rest of the week is work which I've done in collaboration with my PhD student Jacqueline, who is sitting in the back over there. Sorry that I haven't given proper references yet, but yeah, so I'll continue now. I want to use some interesting structures on this cohomology. And the first structure I want to introduce is a cup product. So this just generalizes, generalizes cup products on Czech cohomology. So a cup product denoted by a cup is a map from CP, YM. So it's a way to combine cochains, CP and C, degree CP and CQ. And for this you may need to be able to multiply elements in F. So you can do that for integers or real numbers, etc. And this goes to CP plus Q YM F. And in relation to the earlier question which I got, it turns out that the differential is going to be satisfying a Leibniz rule. So it's going to be a derivation with respect to this product. And the formula is quite simple. Well, I mean, so this is going to generalize the wedge product of forms, right? But then for more general cochains, in particular, you can take it over the integers. So it's going to be some generalization of wedge product, but for chains we can be integer valued. So I need to say how this acts on P plus Q. Now I can of course just take the first P variables here, but well, if I want to take the last variables here, you'll see that I need to start here with yp to have enough variables. And that becomes of the degree shift. But this is the formula, so you just take the product of these two cochains and take the first one here to be equal to the last one. Well, first one here to be equal to the last one there. So it's quite a simple formula. In fact, there exist higher cup products. We call them cup I. They go from CP, and let me not write down the whole thing again, to CP plus Q minus I, such that for I equals 0, you get the cup product there. So this for I bigger equals 0, cup 0 is equal to cup. And now I'm going to write down an extremely beautiful relation. Which is known for about 100 years. It's basically in the paper where these higher cup products were introduced. It's a paper by Steenrod. It's a beautiful paper. Let's see. Maybe I should give you what the cup 1 is. So it's very hard to write an explicit formula for what this cup I actually is. In that paper by Steenrod, it's given in some combinatorial process on graphs. And maybe you can appreciate it when I write down the cup 1, for which there exists an explicit formula. So it's not as simple as this one. This one is really simple. This one essentially you need to get one variable less. So instead of identifying just the first and the last here, you need to identify pairs of elements in these two things. And then the combinatorial thing is that you choose those pairs in a particular way with particular signs. So this is j equals 0 to p minus 1. Particular minus sign, but not an obvious one. And then I take, for each j, I take the elements y0 to yj, and then I take out a string of elements, and I start again with yj plus q, up to y p plus q minus 1, times the g of, and for the g I put in that particular string which I've taken out, but where I leave the first and the last element the same. So I take out strings of length q and identify the first and the last variable of the string that I've taken out, and here's the stuff that was taken out. So it's not an obvious formula.
Can you read the indices once again?
Yeah?
We cannot do
Too small. Which, the indices are too small? Okay, I'll... so, I don't want to... Okay, the specific formula doesn't matter all that much. You can look it up in the notes if you want. I just want to throw this at you to show you that it's not a simple formula. But the next formula is, that I want to write down, is very interesting. Or maybe I'll just give you an example. If f and g are elements of C1, then f cup 1 g should also be an element of C1, 1 plus 1 minus 1. So I should tell you how it acts on y0, y1, and there's just one term in this sum. Well, there's basically one thing you can write down which has two elements equal, so that's indeed what you have. Okay. So here's a theorem which I'm not going to ask you to prove because I haven't given you formulas or even a combinatorial way to compute the higher cup products, but it turns out they satisfy a fundamental identity, which is the last thing I'll write down for today. So if you want to check whether these cup products are commutative or anti-commutative or graded commutative, well, so the wedge product, for instance, on forums is graded commutative. So the sign here is PQ minus I. So F is an element of CP, G an element of CQ. So G cup I minus 1 F. It turns out to be, well, another factor here, P plus Q minus I. And then you have the delta of F. And then on the right-hand side, it's all cup I products, minus del F cup IG minus 1 to the power P F del G. So for instance, for I equals 0, there's no I cup minus 1, so then the left-hand side is 0. So for I equals 0, it tells me that delta is a derivation of the cup product, a graded derivation. If I look at I equals 1, then it tells me that this cup product, usual cup product, is not graded commutative, but this is the violation. The violation is given in terms of the cup 1. But the beauty of this formula is that it sort of links the fact that the violation of the graded commutativity is related to the deviation from del being a graded derivation of the cup product 1 order lower. So this is a beautiful formula, and I'll be using this a little bit, I guess, on Thursday, but I think it's time to stop here. Okay, thank you.